Section 2.3 is polynomial functions of higher degree with modeling. In Section 2.1, we talked through some linear and quadratic functions in modeling. This section deals with those polynomials as well as some others of higher degree. This first f of x equals equation is showing you just the basic form for a polynomial. Long story short, it has to have non-negative integer exponents, which means they can't be negative and they can't be fractions, and all the way down to a constant term if there is one. Each monomial is a term. Terms are in order of decreasing degree. That's what we call standard form. So you would always want to start with the highest exponent first, down to the lowest exponent, and then finally ending with your constant term. A sub n x to the nth is what we call the leading term, and then a sub 0 is what we call the constant term. So if it ever asks for the degree of the polynomial, you're looking for the highest exponent. The leading coefficient is the coefficient of that term. So if you were to look at the graphs of x squared, x to the 4th, x to the 6th, x to the 8th, so on, any polynomial with an even degree, you should notice that the arrows are always pointing the same direction. Now for the ones that I've listed where they are positive leading coefficients, both arrows would be pointing up. But if you put a negative in front of those, both arrows would be pointing down. What you need to notice is that the arrows point the same direction. If you look at the graphs of x cubed, x to the 5th, x to the 7th, x to the 9th, any polynomial that has an odd degree, you should notice that the arrows point opposite directions. And depending on whether that is leading coefficient is positive or negative would depend on whether it points down to the left and up to the right or vice versa. But what you should notice is that the arrows point opposite directions. So just to make sure that we are clear on what these arrows are going to look like, we're going to come back and fill in some of the important details in between. But just to look at the arrows, if n is odd, so the degree is odd, and the leading coefficient is positive, the arrows are going to point like this. For the n's, looking at the n behavior of the graph, the arrows are going to point down to the left and up to the right. If the degree is odd and the leading coefficient is negative, which is what that less than 0 means, negative, then to the left it's going to be pointing up and to the right it's going to be pointing down. And again, that's for any odd degree polynomial. It could be linear, could be cubic, could be degree 5. Alright, if n is even, so the degree is even and the leading coefficient is positive, both arrows are going to point up. And similarly, if the degree is even and the leading coefficient is negative, both arrows are going to point down. Alright, so that is one important thing that we have to be able to fill in when we're sketching graphs by hand, which is going to be our ultimate goal. We have to know which direction the arrows on the end are going to point. Alright, this slide talks about how polynomial functions are smooth and continuous for all real numbers. So they're going to be nice, smooth, no jumps, no holes, no asymptotes. If the degree of a polynomial function is n, then the function has at most n zeros. So whatever the degree of the function is, it can only have up to that many zeros. So a degree 3 can have up to 3 zeros. Now that does not mean it has to have that many. It can have at most that number of real zeros. If the degree of a function is n, so same deal, then the function has at most n minus 1 local extrema. In other words, maxes and mins. So if the degree is 3, it can have up to 3 zeros, but it can only have up to 2 maxes and mins, or extrema. 1 less than the degree is the most I can have as far as maxes and mins. So a couple examples, like I just mentioned, cubics can have at most 3 zeros and 2 extrema. Quartic, which is degree 4, can have at most 4 zeros, and 3 extrema. Alright, so our first example here says sketch a graph of the following functions, and the only things that we're going to worry about right now is the end arrows. We're going to make sure that those are pointing the correct direction. We are going to put the y-intercept at an appropriate place, and we're going to make sure that we don't have too many zeros and too many maxes and mins. So this is a degree 4, so it's an even degree, and it has a positive leading coefficient. So from the very beginning, I know that the arrows for the ends are both going to point up because it is an even degree with a positive leading coefficient. Both of the arrows are going to point up. Alright, then I look at the y-intercept, and how we get y-intercept is we plug in 0 for x, which is going to be pretty easy for all of these terms that have an x. Those are all going to be 0. So I'm showing this step, and then from here on out you don't really have to do this. 0, 0, 0, 0, 35. So the y-intercept is going to be 35. And really what you can do is just cover up any of the terms that have an x. If you plug in 0, those are going to go away. So it really is just always going to be that constant term. So this one is going to cross the y-axis at positive 35. Now you don't have to put 35 dashes. Let's just put a dash somewhere and put a 35. We don't even need a scale, anything like that, but we're going to say that this graph is going to cross the y-axis at positive 35. Alright, now the only other thing we need to do is just fill this in, make it smooth, make it curved, no jumps, no vertical asymptotes, anything like that. And we also have to make sure we don't have too many zeros or maxes and mins. So one possible out of many, one possible way this could look would be like this. Okay, now again, just taking the arrows that we had on the ends, taking the y-intercept that we had already plotted, and then just making sure we have 1, 2, 3, 4 zeros and no more. We have 1, 2, 3 extrema and no more. Alright, so again, this is not the only way that this graph could look. This is one of many possibilities for how this could look. Another example, very similar. This is an odd degree. This is degree 3 with a negative leading coefficient. That tells me the arrows are going to be up to the left and down to the right. And the y-intercept, if I plug in 0 for all of these x's, the y-intercept is going to be 12. So I'm just going to put a 12 on here. Alright, and then I just have to fill in, making sure I don't have too many zeros and too many maxes and mins. So I'm going to go like this. Alright, now you might look at that and say, but that only has 1 0. Even though this is degree 3, it does not have to have 3 zeros. It can have at most 3 zeros. So 1 0 is fine for this cubic. It only has 1, 2 extrema, so no problems there. So this is one way this could look. If you had drawn this to have a 0 here, a 0 here, and then the same 0 that I have, that is also correct. Alright, real zeros are the x-intercepts of the graph of a function. In other words, solutions to f of x equals 0. So if we set the function equal to 0 and solve, that's how we can find real zeros, and those are the ones that you can see when you graph it. This says find the zeros of the following function and sketch its graph. So we're adding to the tools that we already have with the arrows on the ends, with knowing where it crosses the y-axis. Now we're going to make sure that it crosses at the correct places on the x-axis. Alright, so on this one what we want to do is set it equal to 0 and solve. And how we're going to solve this is by factoring, and I would always try factoring first. We might run into some cases where factoring doesn't work and we'll have to use another method, but I think for this one factoring does work. We can factor out an x, GCF of x, because all three terms have an x. When I factor that out, that's going to leave me x squared minus x minus 6. And then that quadratic will factor again to be x minus 3 x plus 2. X minus 3, x plus 2. Alright, so this gives me 3 real zeros. This first one, if I set it equal to 0 and solve, it's already solved, so x equals 0. X minus 3 is going to give me a 0 of 3. And then this x plus 2 factor is going to give me a 0 of negative 2. Alright, so now we have some particular points on our x-axis that this graph is going to go through. It's going to go through 0, it's going to go through positive 3, and it's going to go through negative 2. Alright, now we need to put that together with the things that we already know. Now this one is going to have a y-intercept of 0, because if I plug in 0 for the x's, I'm still going to get 0, which makes sense that I already have a point there. This is an odd degree with a positive leading coefficient, so I know the arrows on the sides have to go down to the left and up to the right. And then I just have to draw in a graph that fits that. Alright, so as far as where these maxes and mins are, this max here and this min here is not important, and a friend of yours might have drawn theirs to have a much higher max or a much lower min. For right now, we're not concerned about that. We're actually not going to be concerned with that in pre-calculus at all. You will be concerned with that in AP Calculus, knowing exactly where those maxes and mins are. But for now, we're just concerned about the arrows, the y-intercept, and any real zeros that we can easily find. Alright, one last thing that we're going to talk about on this video is something called multiplicity. Now this first function is already written in its factored form. F of x equals x minus 2, all of that cubed. That means there are actually 3 of those factors, x minus 2, x minus 2, x minus 2. And then there's this x plus 1 quantity squared, which means there are 2 of those factors. So there are actually 5 factors here, which means the degree of this function would be 5. I do know that its leading coefficient would be positive because we have this x cubed times this x squared, and both of those are positive, so its leading coefficient is going to be positive. So when you have a factor that is repeated, we call that having a multiplicity. So if I were asking you what are the zeros of this function, well, there is a 0 at 2. That has a multiplicity of 3. Because that is repeated 3 times. There is another 0 at negative 1. That has a multiplicity of 2 because it is repeated twice. So those multiplicity numbers come straight from those exponents, or how many times that factor has been repeated. And that is what we call multiplicity. Now, what that tells us about the graph, and again, just adding one more tool that we can use to help us sketch graphs by hand and not rely on our calculator. If a 0 of a function has an odd multiplicity, 1, 3, 5, 7, 9, then the graph of the function crosses all the way through the x-axis at that point. So an odd multiplicity means the graph crosses all the way through. If a 0 of a function has an even multiplicity, 2, 4, 6, 8, so on, then the graph of the function just touches the x-axis at that point. It does not cut all the way through it, it just barely touches the x-axis at that point. Alright, last example on this video to use what we just talked about with multiplicity. It says find the zeros and sketch a graph of the function. So we're putting all of this together. First of all, since we just talked about zeros and multiplicity, let's write that down. This one has a 0 at 3, multiplicity of 2. It also has a 0 at negative 2 with a multiplicity of 4. The degree of this function, because we do have an x squared times an x to the 4th, the degree is going to be 6. And because the coefficients for both of these x's are positive 1, we know that the leading coefficient is going to be positive. So as far as arrows, I know that they are both going to point up. Even degree, positive leading coefficient, both arrows are going to point up. Alright, I also know that at negative 2, there's a 0, and at positive 3, there is a 0. But at those places, because both of them have an even multiplicity, the graph is just going to barely touch the x-axis at those points.